In the last class on Tuesday, we were talking about the mathematical formalism for quantum mechanics. And so it's a formalism, a mathematical framework where wave functions correspond to vectors. Right, so these things are vectors in Hilbert space. And this construction that I was talking about as an integral sandwich is an inner product of vectors. And what else? And then any observable quantity like position or momentum or energy corresponds to an operator. And in particular, it is a Hermitian operator, which is a term that I defined for you, which means an operator that we could just call it Q hat in general, and it satisfies the equation that psi, the inner product of psi with q psi is equal to the inner product of q psi with psi. Okay, so it's a subset of operators, a special type of operator. And Tuesday, I gave you some examples of operators and showed you some that are Hermitian and some that are not Hermitian. Okay, so the plan for today is I want to do a few more general comments, right? So I gave you a bunch of general definitions, which are not the most exciting thing for a class, but and then I gave up and did some examples on Tuesday. So now I'll do a few more general comments and then a few more examples. And then after that, towards the end of today, I'm actually going to calculate something. And so we'll finally find a use for all these definitions that I'm setting up here. Okay, so that's for today. All right. For a few more general comments, okay, and so one comment is, let's see, if an operator is Hermitian, okay, if Q is Hermitian, we know by definition that the definition is that, as I just wrote, Q psi inner product with psi is equal to psi inner product with q psi for all psi, right? For all vectors in Hilbert space. But it is possible to prove some extra thing, right? We can prove something that's even stronger than this thing. Here, I'll call it a theorem. That makes it sound fancy, doesn't it? Okay, I'll call it a theorem. That not only is that true, but also then if you have any two functions, f and g, then the inner product of QF with G is equal to the inner product of F with QG for all F and G. Okay, so this statement, this theorem, is a little bit stronger than the original definition, right? The original definition works if there's the same function in both of these places, okay? But this theorem works even if you have different functions in those two places, F and G, okay? And the proof is going to be a job for you in the next homework. Not the one that you're working on now, but the one that comes after that. And the assignment from the textbook has hints about how to prove this. Okay, so I'll be using that, right? So this stronger statement that if Q is Hermitian, then you can move it from one side of the inner product to the other, even if there are different functions F and G on the two sides. Okay, another general comment. If Q is not Hermitian, if it's some other kind of operator that's not Hermitian, then it has a partner operator, which is called a Hermitian conjugate. Which is written like this. And this symbol up here is called a dagger, right? And so people pronounce this as Q dagger. Right? And so if Q is not Hermitian, it has the conjugate, Hermitian conjugate Q dagger, such that Q dagger acting on F, inner product with G, is equal to F inner product with QG. And likewise, Q acting on F, inner product with G, is equal to the inner product of F with Q dagger G for all F and G. So that is to say, if Q is not Hermitian, then if you try to move it from one side of the inner product to the other, it doesn't quite work, right? That you don't get the same operator showing up on the other side, but you get this partner operator, the Hermitian conjugate that shows up on the other side. And vice versa, if you have a Q dagger here and you try to move it to the other side of the inner product, it's a Q that shows up on the other side of the inner product. Okay, so this works for all operators, right? That if you try to move it from one side of the inner product to the other, you get something, but it's not necessarily the same operator. It's this partner, the Hermitian conjugate. Right? So that means that a Hermitian operator is its own conjugate. Its own conjugate. So Q equals Q dagger. Okay, so if it's a Hermitian operator, then Q and its partner, Q dagger, are the same thing. But if it's not a Hermitian operator, then Q and Q dagger are different things. One word that you might sometimes see for that is self-adjoint. That adjoint is another word for Hermitian conjugate. And so if an operator is its own Hermitian conjugate, then it is self-adjoint. Okay, two more general comments. What if you combine operators, right? We've done some things earlier in the semester where we were composing operators, right? We let one operator act and then we let another operator act, okay? So now let's see what happens if we put a pair of operators like that into an inner product. So if we want to combine two operators, for example, let's call them Q and R. Okay. So suppose we want the Q acting on R, acting on F, and take the inner product of that with G. Okay. So you remember, this is like a notation that we used earlier in the semester, right? That R acts on F, right? So F goes into R, right? And then the output from R goes into Q. So suppose we want to know what is the Hermitian conjugate of this combination QR. Okay. So if we have QR acting on F, now let's try to put that onto the other side of the inner product. We could interpret this as Q acting on RF. Okay. So this is an inner product, right, where Q is acting on one function, RF, and that is taking inner product with G. Okay. So this is equal to RF inner product with Q dagger acting on G, right? That is, we move Q to the other side of the inner product and it turns into Q dagger. Now, let's move R to the other side of the inner product. Okay. So this is then equal to F inner product with R dagger acting on what was already over here. What was already over there is Q dagger G. Right? So R dagger is acting on Q dagger G, like this. Okay. And now we don't really need the parentheses on the right side. So that's F acting on R dagger, Q dagger, G. Okay, so this then tells us that the combined operator, QR, it can move to the other side of the inner product and it turns into R dagger, Q dagger. All right. So that is, if I erase this parentheses here, oops, let's try that again. R dagger F, right? I could call this is the same as moving Q dagger, excuse me, moving QR to the other side of the inner product, and we get R dagger Q dagger, okay? So that means that the Hermitian conjugate of QR is equal to R dagger Q dagger. So QR quantity dagger, okay? So the Hermitian conjugate of QR, so QR all dagger, right, is equal to R dagger Q dagger. Okay, so this tells us how to make the Hermitian conjugate for a pair of operators, right, that are combined together. Right? And you may have seen something like this before in your life in a linear algebra class, right, when you were working on the transpose of a matrix. Right? And so if you have two matrices, so if you have two matrices, let's say M and N, okay, and you do matrix multiplication, Mn, okay, and then you want the transpose of this matrix, Mn transpose, and that comes out to be equal to the matrix product of N transpose with M transpose. Okay, so that means you transpose both of them, but you also need to change the sequence, right? That what was last becomes first and what was first becomes last, okay? So it's like that with Hermitian conjugates also. Okay? And the general lesson is that Hermitian conjugate is equal to complex conjugate and transpose. You know, this point that I was just illustrating on this slide, right, of showing that if you have a combination of operators and you do a Hermitian conjugate, you need to switch the order. That's the transpose part, right? But also, I showed you that, you know, if you're multiplying by I, it changes to multiplying by negative I, right? That's the complex conjugate part, right? And so doing a Hermitian conjugate is like doing both kinds of switches, right? It's transpose from the matrix point of view, and also complex conjugate from the complex number point of view. Okay. So yeah, so a Hermitian conjugate includes both of those two concepts. Okay, those are my general comments. Are we kind of good so far with those things? All right. Now what? Now, let's see here. Let's do some more examples. Okay, so I showed you some examples of figuring out whether operators are Hermitian or not. So my first example was, just multiplying by 2. And the answer is yes, that is Hermitian. Okay. Multiplying by I, no, that's not Hermitian. Right? And if that is to say, if we were to take the Hermitian conjugate of multiplying by I, you get multiplying by negative I. So I could write that with the notation, the dagger notation I just showed you, as I dagger is negative I. Okay? Whereas 2 hat dagger is just 2 hat. And then a couple other examples, okay? X hat we did. That is, yes, Hermitian, okay? So X hat dagger equals X hat. And then we did d by dx hat. And the last thing I showed you on Tuesday was, no, this is not Hermitian, right? And we figured this out using the integration by parts trick, right? That if we calculate the inner product by using integration by parts, we could prove that the Hermitian conjugate of d by dx is negative d by dx operator. Okay, now let's try a new operator. Okay, how about momentum? Okay, so you remember that the momentum operator is negative I h bar d by dx hat. Okay, so suppose we want to know, is this Hermitian? Okay, so let's figure out the Hermitian conjugate of that. Okay, so P dagger. So, when we have a combination like this, okay, we want to just take the Hermitian conjugate of each thing there and reverse the order. Okay, so this is d by dx hat dagger, and then h bar dagger, and then I dagger, and -1 dagger, right? So each of those multiplications. Right? So the Hermitian conjugate of d by dx, so we just figured out there, it's d by dx, but with a negative sign. Okay? So that is negative d by dx. Okay. The Hermitian conjugate of h bar is just multiplication by h bar, right? H bar is Hermitian because it's a real number, like 2. So it's just h bar. Okay. The Hermitian conjugate of multiplication by I is multiplication by negative I, right? That's right up there. So this is multiplication by negative I. Okay. The Hermitian conjugate of multiplication by -1 is just multiplication by -1 because -1 is real. Okay, so now you can see that the negative sign from the conjugation of the derivative just cancels the negative sign from the conjugation of the I. Okay? Those things cancel, and then we get this set of factors times d by dx. And those factors can factor out to the front because those are just multiplication by a constant. Right? So this is equal to negative I h bar p, whoops, excuse me, ha ha ha. Yeah. It's negative I h bar d by dx hat, and that is p dagger. Right? And so the momentum operator is, what am I doing? And that's equal to P. So the momentum operator is Hermitian, right? That if we go through this argument, we get that the conjugate, the Hermitian conjugate of P is equal to P. Right? So the extra minus sign associated with conjugation of the derivative cancels the minus sign associated with the conjugation of the I. Right? And so P is a Hermitian operator. Yes. And that's good, right? It's good because momentum is an observable quantity, right? And I claimed to you before that any observable quantity has to correspond to a Hermitian operator, right? And so this is a nice example of that, right? So like with position, this position is one observable, yes, and momentum is another observable. Okay, so these things both correspond to Hermitian operators. Okay, let's do one more example like that. Let's do the raising and lowering operators for the harmonic oscillator. Okay, so for the harmonic oscillator, you remember we have these raising and lowering operators, right? So A plus or minus is equal to 1 over the square root 2h bar m omega, and then minus or plus I p hat plus m omega x hat. Okay, so suppose I want to know, are these operators Hermitian or not? Okay, well, let's figure that out. Okay, so suppose I want to know what is the Hermitian conjugate of A minus. Okay, so what is A minus dagger? Okay, what is A minus dagger? Okay, so let's figure it out. Okay, so that is, I have this factor 1 over 2 h bar m omega. This is a real number. Okay, it's a real number, so it can just factor out, and a real number is its own Hermitian conjugate. All right, and now, so A minus is I p hat plus m omega x hat. And I want to know the Hermitian conjugate of all of that stuff. All right, so that is 1 over this square root. So here it's the Hermitian conjugate of P times the Hermitian conjugate of negative I plus the Hermitian conjugate of X and the Hermitian conjugate of m omega. Okay. Well, the Hermitian conjugate of P is just P. The Hermitian conjugate of negative I is positive I.
Dr. Selinger,
Yes.
for A minus, shouldn't that be a positive IP?
Yes, you're right. I knew I was doing something wrong. Thank you. Okay, let's fix that. A minus is positive IP. Okay, excellent. You saved me. All right. So I want the Hermitian conjugate of I. And the Hermitian conjugate of I is negative I. Aha, much better. Okay, then what? The Hermitian conjugate of X is X. The Hermitian conjugate of M omega is M omega, because M and omega are real numbers. So now I can just simplify this by moving the constants back in front of those operators. So I get negative I p hat plus m omega x hat. Aha, and here with the negative I, that is equal to A plus. Okay, so A minus is not a Hermitian operator. Its Hermitian conjugate is A plus. Okay, and vice versa, if you run the same argument in reverse, then the Hermitian conjugate of A plus is A minus. So A plus and A minus, they're Hermitian conjugates of each other. Okay, and in fact, some books use a different notation. Some books use the notation where A minus is just called A, and A plus is just called A dagger. Okay, so meaning Hermitian conjugate. Okay, so you will often see that in other books, not the Griffiths textbook, but if you go on to other courses, you might see that. Okay, so these are a few examples of things. Good. All right. Now, this is laying out the general framework, the general formalism for how do we express operators. Okay. Now let's calculate something. All right. So I want to actually find something useful here. Okay. And so what can I calculate? I want to use this as a way to think about uncertainties. Okay, so if we have any observable Q, okay, so this is a Hermitian operator. Suppose I go to make an observation of this. In some state psi. It has an average. It also has a standard deviation. That's the kind of thing that we've been studying all through the semester. Okay, so the expectation value the expectation value of Q in the state psi is this expectation value of Q, like that. So that is the inner product of psi with Q psi, right? This is a compact way of writing our integral sandwich. Okay. Now, what about the uncertainty? Okay. So the uncertainty in Q is given by this sigma Q squared. So that's the average of Q squared minus the average of Q quantity squared. All right. So that is the inner product of psi with Q squared acting on psi minus the inner product of psi with Q psi quantity squared. Okay, now if I want to write this maybe a little bit more compactly, let's suppose that the expectation value is what I will call little q. Right? So then this is psi q squared psi minus little q squared. Okay, now here's the thing for this calculation. Suppose I'm a person who hates uncertainty, right? I got to be sure about things. I can't stand uncertainty, right? When will this pandemic be over? I have to know. I can't stand the uncertainty, right? I really want the uncertainty in Q to be 0, okay? Suppose I want no uncertainty. Okay, so that means I want this uncertainty in Q to be 0. Okay, so what kind of relationship between Q and psi would give us a situation like this, where there's 0 uncertainty? Okay, let's work that out using all the stuff that we've proven here. Okay, so we know that's equal to this combination right here. Okay, so that is equal to psi inner product with Q squared psi minus this Q, little q squared. All right. I'm going to rewrite this in a clever way. Okay, so let's rewrite this as psi with Q squared psi minus, well, 2Q squared, a little q squared plus a little q squared. For sure I could do that, right? And now for this 2 little q squared, let's see, I will write that as, here, I'll just write that term. I'll write that term as minus 2 expectation value of Q times Q. Well, because little q is the expectation value of big Q. Right? Or I could write that as minus 2 inner product of psi with Q psi all times Q. Okay. Okay. And now that means I can now combine them into one big inner product. This is the inner product of Q squared minus 2 Q operator times little q plus little q squared acting on psi. Does this work for you guys? Right? I mean, you can see how I get from one to the other, right? It's easier to see going backwards, right? That the first term is psi inner product with q squared psi, right? That goes there. Then the second term, we have constants, -2 and little q, so -2 and little q, times the inner product of psi with q psi. The third term is q squared times the inner product of psi with itself, right, which is 1 for some normalized wave function. Okay. So, you sort of believe this? All right, I can keep going. Okay. So, this is equal then, well, we can recognize this operator in parentheses here. This looks like a square, right? This looks like, whoops, the inner product of psi with q minus little q squared acting on psi. Right. So remember, little q is just a number. Little q is the expectation value of the operator big Q. Okay, now let's keep going. Let's now say, well, we have the operator big Q minus little q, right? This is an operator which acts on psi twice, right? So this is an operator, this all is equal to psi, then we have big Q minus Q, big Q minus little q, acting on psi like that. Okay, this is what we want to be equal to 0. Now, let's take this combined operator, the big Q minus little q operator, and move it over here. We can do that because it's Hermitian, right? That big Q is Hermitian and little q is just a real number. It's Hermitian. So the difference is Hermitian, so it can move to the other side of the inner product. So this is big Q minus little q acting on psi, inner product with big Q minus little q acting on psi. Okay, so that tells us something special about the operator big Q minus little q acting on psi, right? Let's call that combination, let's call that combination F. Big Q minus little q acting on psi is F. Over here, that's F. So this is the inner product of F with F. But you remember, one of the things that I showed you on Tuesday is that the inner product of any function with itself is greater than or equal to 0, and it can only be equal to 0 if the function f is 0 everywhere. All right, so therefore f equals 0 everywhere for all x. But this difference, big Q minus little q acting on psi, that's F, okay? Therefore, big Q minus little q acting on psi is equal to 0 everywhere. But big Q minus little q, well, I'll distribute that now. That is Q psi minus little q psi equals 0 everywhere. So if I want to write that compactly, I could just say big Q hat acting on psi is equal to little q times psi everywhere. Okay, so this is the relationship that I was looking for. Okay, so this tells us that if we want a situation with no uncertainty, right, a situation where there is a specific value of an operator, of an observable, right, and no uncertainty in what that observation is going to come out to be, then we need to have this relationship between the states, between the state psi and the operator, okay? That the operator acting on the state is just a number times the state. This is a mathematical relationship which goes by the name of an eigenvalue relationship. This is an eigenvalue equation that Q acting on psi is equal to little q times psi. Okay. So here, this number, little q, is called an eigenvalue. Okay. And this this function psi, this is called the eigenvector. Right, so you remember that functions correspond to vectors, right, in this Hilbert space concept, right? And so an eigenvector could also be called an eigenfunction. Okay, so this is saying that there has to be a special relationship between the operator Q and the wave function psi. Okay, so we would say that psi is an eigenfunction of Q with eigenvalue little q. Right, those are the words that go along with this relationship. So in this relationship, the eigenfunction is something which is for sure not zero. It is a state of the system which is normalized or can be normalized. The eigenvalue might be zero. Might be any real number. So if we have this special relationship between the function psi and the operator big Q, then no uncertainty. All right. But in the generic case where we don't have this relationship, then yes, there is some uncertainty. Okay, so I can show you a couple examples of how that works. So for example one, what if the operator is the Hamiltonian, so the energy operator? Okay, so the way to have a state with a definite energy is if the Hamiltonian acting on the state is equal to the energy times the state. Okay. So this is an equation that we have seen before in this class, right? This is the time independent Schrodinger equation. So when I first showed you this equation a few weeks ago, it was just, look, here's a nice trick for solving Schrodinger's equation, right? To do the separation of variables. But now with this mathematical formalism, we see that it's more than just a nice trick, right? It's also expressing something special about the wave function and the Hamiltonian operator. Okay, so it is expressing that psi is an eigenfunction of the Hamiltonian with eigenvalue E. So people will sometimes use the words that psi is an energy eigenfunction and E is an energy eigenvalue. Okay, and so this is telling us that, if we have one of these special solutions of the time-independent Schrodinger equation, then there is a definite energy, that there's no uncertainty in the energy. And remember, you already knew that, right? You already knew that if we have one of these special solutions for the time-independent Schrodinger equation, there's an energy, because we've been calculating it in all the examples this semester, right? That if we have the particle in a box, for example, right, that we have a bunch of these special solutions, and there's solution one with energy one, solution two with energy two, etc. Right? And so now we can interpret that as saying the Hamiltonian has a bunch of energy eigenfunctions with corresponding eigenvalues. Right? And so we can make a list of the energy functions and the energy values. That's what we've been doing in this problems that we've solved. Okay, then for another example, okay, let's think about the momentum of a free particle. Okay, so you remember the way I like to talk about free particle states, right? Where I consider a state in a finite volume and then take the limit as the volume goes to infinity. Okay, so if I do it my way, I would say that the wave function is 1 over the square root of the system size times e to the I k x, right? You remember this from free particles? This was our solution back then. Okay, and now what happens if we have the momentum operator acting on psi? You remember the momentum operator is negative I h bar d by dx, and that's acting on psi. So that's 1 over the square root of L e to the I k x. So let's work this out. Okay, this is a function that we can differentiate. Okay, so we get negative I h bar, the 1 over root L factors out. And then the derivative of e to the I k x is I k times e to the I k x, like that, right? All right. And then we can combine these factors, and the negative I cancels the I. And so we get h bar k times 1 over root L e to the I k x, which is h bar k times the function psi. Okay, so this is the eigenvalue relationship. Okay? So the words we would say are psi is a, well, it's an eigenfunction of momentum with eigenvalue h bar k. Okay, or in other words, psi is a momentum eigenfunction, and h bar k is the corresponding momentum eigenvalue. Okay, so this then is a state that has a definite value of the momentum. Right? This is something that has a definite momentum, the same way that back in my example 1, there's a definite energy, right? And back in the general thing, we would say there is a definite Q, whatever Q might be. So a word for this, a state with no uncertainty, is called a determinate state. So a state with a definite Q. Okay, and so it turns out we've seen a couple examples of determinate states before, but now it's a general concept in this Hilbert space notation. So this now is one thing that we get from doing the mathematical formalism, right? It's knowing when can there be a determinate state as opposed to a state with some uncertainty. And the answer is when there's this eigenvalue relationship. Okay, so now I'm sitting here speaking as if you know what I'm talking about with eigenvalues and eigenvectors. But I should probably get some feedback from you guys because I'm never quite clear on what the math department has taught people. And so has the math department in fact taught you guys about eigenvalues and eigenvectors? Okay, so let me put somebody on the spot here. How about Ryan? I see you sitting there. Ryan, tell me something about what the math department has told you about eigenvalues and eigenvectors.
Well, we went over them a lot. I don't entirely remember too much about them because it was a few years ago. So yes, I've been exposed to them, but I couldn't really say much about them, to be honest.
Okay. Did you ever cover those in a physics class?
I don't believe so.
You don't believe so. Andrew, have you ever seen eigenvalues in a physics class?
Yeah, well, I had math methods, the senior level course with Dr. Sprunt, and we talked about them there, and we also talked about them in your classical mechanics class.
Oh, good. You remembered that. I was scared that you were going to totally forget that we talked about it when I did classical mechanics. Right. So in classical mechanics, this kind of thing comes up, say, with coupled harmonic oscillators, right? That if you have a bunch of harmonic oscillators coupled together and you want to figure out about the normal modes, right? Then calculating the eigenvalues and eigenvectors of a matrix is a useful way to do that sort of thing. Okay, good. Have any of you ever seen eigenvalues and eigenvectors in E&M class? Is that something that people talk about? Maybe not so much. Okay, I mean, there are situations in optics, but maybe it comes along in more advanced classes. All right, never mind that. quantum mechanics uses it a lot, right? So for quantum mechanics, we use this concept a lot. And so I'm just kind of introducing it now. And but we should talk about that in general, okay? So we should talk about what eigenvalues and eigenvectors, both for matrices and then this generalized concept to operators, okay? Well, let me just kind of start that now. I was planning to do it next week, but let's just begin now briefly, because I've got maybe 5 or 10 minutes left. Okay. So suppose we want to talk about eigenvalues and eigenvectors. Okay, and so let's think first about matrices. Okay, so what if we just have a 2x2 matrix? Okay, so if we have a 2x2 matrix, and let's suppose it is a Hermitian matrix, meaning that it is equal to its complex conjugate transpose. So one example would be a matrix that is real and symmetric, like this. Okay. Another example would be 0, 1, 1, 0. Another example would be 0, I, negative I, 0. Okay. So you can certainly see, right, if you have a matrix like A, right, if you take its transpose, you just get A, right, because it's all symmetric about the diagonal like this. Okay. And then if you take the complex conjugate, you still have A, right, because it's all real. With B, this is also real and symmetrical. With C, it is not real, it is not symmetric, but if you take the transpose, C transpose is 0 minus I, 0. And then C dagger is the complex conjugate of the transpose. So it is 0, I, minus I, 0. Okay, so these are 2x2 Hermitian matrices. Okay. So we want to know about the eigenvalues and eigenvectors. Okay, so we want to know what are the vectors V such that, for example, the matrix product of A acting on V is equal to lambda V, right? Or B acting on V is equal to lambda V, or C, right? So, let's try to figure out an example. Okay, so what if you are working with the matrix A, for example? Okay, so can any of you remember how can you tell me what are the eigenvalues of A? Okay, this is a trick question because it's easier than it sounds. Okay, so my trick easy question is the eigenvalues of A. All right. That is meant to be a trick question because finding the eigenvalues of a matrix is supposed to be related to putting the matrix into a diagonal form. But A is already in a diagonal form, right? That all the off-diagonal elements of A are 0. So the trick answer is supposed to be that you can look at it and say, oh, the eigenvalues of A are the things on the diagonal. So 1 and -2. Okay. I'm guessing maybe you guys could use a little refresher on eigenvalues and eigenvectors. Okay, let me try to prepare that for Monday, okay? I'm gonna do a little refresher on eigenvalues and eigenvectors of a 2x2 matrix, and then move on to eigenvalues and eigenvectors of an operator in quantum mechanics. So like the energy or momentum, things like that. Great. Okay, we'll do it. I'll stop for now and let's pick up on Monday. And you remember you'll have a homework for me on Monday. Okay, have a good weekend, you guys, and I'll see you then.